So welcome to all. Myself Dr. Santhosh Singh, working as an Associate Professor in Department of Physics, Institute of Aeronautical Engineering. Today I am going to discuss about characteristics of quantum well structure. Means in my last video lecture I already derived the expression of density of the state for quantum well structure. So based on that derivation, that expression, we can discuss some features about quantum well structures. Okay, let's start. So what we derived in my last video lecture, density of states in quantum well structure is kT dkt upon pi upon Lj. Okay. So see, this is the depends on kT, means this expression is in term of k. So you already know density of state rho k is equal to rho e also. Means you can express the density of a state either in term of k or in term of e. But generally for derivation we use the wave vector k for deriving the density of a state. Then later we convert from this derived expression, we can got the density of a state in term of energy. Okay. So we will see, we will convert this expression in term of energy also. So what you know that rho k dt dk, rho k dk is equal to rho e de. Okay, means number of available states in the range k to k plus dk per unit volume is known as density of state, or in term of energy, number of available state in the energy range E to E plus D per unit volume is known as density of state. And this is for bulk case. But we are discussing about quantum well structure, and in quantum well structure, you know that the one dimension is confined. And in our case, I confined my z direction. I confined the z direction, means the crystal cannot grow along the z direction. Okay. And for that, what we wrote? We wrote one expression of energy E is equal to, generally in bulk case, E is equal to EC plus H cross square K square upon 2 MC. I am considering the case for conduction band. But if you confine the z direction, this is for bulk case. But if I confine, anyone confined there any direction, in my case, I chosen the z direction. So what happens? This expression will convert into, you know that this k is also, k vector have a three component kx, ky and kz, and now you are confining the z direction, means the z value cannot change. Okay, it will change, but for particular z, for single z, only x and y, the transverse component of z will change. So how this value will change? E is equal to EC. Now this hk square, here the k have three components, so you can write h cross square kx square upon 2 mc, where mc is effective mass of electron, h cross square ky square upon 2 mc plus h cross square kz square upon 2 mc. So where you will get the change, where the value will change? Here in x and y component. This component and this thing will constant. So what you can write? this energy expression E is equal to EC plus H cross square kz square upon 2mc plus, you can write this whole expression h cross square kx square plus 2mc plus h cross square ky square 2mc as a, why? Because this is a transverse component, so you can write this whole term in term of kt. Kt is nothing but kt is kx plus ky, transverse component. So E is equal to EC plus h square k z square upon 2mc. You can write simultaneously h square k square kt square plus 2mc. So see here, this whole term is constant. Only the variation is in kt. Okay. So I already derived this expression density of state in term of k, and now I want to convert this density of state relation in term of E. So what we have to do? We have to write, as you know, rho k dk is equal to rho E dE. But here in quantum well structure, this k is nothing but rho kt. Why? Because only in the transverse component you will get the change. So rho k dk t is equal to rho E dE. And what is kt? I already discussed. Okay, so don't be confused. Now let's omit this expression of. Now what you want? You want rho E, density of state in term of energy. So from this expression, this is equation 1. Rho E is equal to rho kt upon dE by dkt. Right? This is your equation number 2. Now, what is rho kt? Actually, this is rho kt. So rho kt is this value. Rho kt is rho kt is rho kt kt upon pi multiplied by Lz. Pi multiplied by Lz. Okay. So this is actually rho kt dkt. So well, if you are considering only rho kt value, so its value will be kt, where t is suffix, upon pi multiplied by Lz. So put this value here. So rho E is equal to rho E is equal to, now I am putting the value of rho kt, means k t upon pi multiplied by Lz whole divided by dE by dkt. Now, what is the dE by dkt? So this is your relation of energy for quantum well structure. This relation. From this relation, I already wrote the expression in term of t. What I wrote? E is equal to EC plus h cross square kz square upon 2mc. These two terms are constant, plus in term of transverse component, means x and y, you can write it for x and y simultaneously kt h square kt square upon 2mc. Now this is your constant. So dE upon dkt. So take the dif first order differentiation. So what we'll get? This is the constant. So this term will go to 0. Now from here dE by dkt. So this 2 and 2 cancel. What you will get? H square kt upon mc. So dE by dkt is what? H square kt upon mc. So you, in the place of dE upon dkt, you can write H square kt upon mc. Now kt and kt cancel. What you will get? Density of state for quantum well structure in term of energy rho e is equal to, this mc will go in numerator, mc upon h cross square multiplied by pi upon Lz. So this is your density of state expression for quantum well structure in term of energy. Okay. And see here, there is no energy term. Means your density of state will be constant. Okay. Why? See, your density of state in quantum well structure will be constant. Why? Because there is this Lz is dimension of your, say, specimen in z direction. This is constant. This is the effective mass of electron in conduction band. This will be also constant. H cross square is also constant. Pi is constant. So density of state is constant in term of energy. Okay, there is no energy expression in density of state. There is no energy term involved in density of state expression for quantum well structure. Okay. Comparison to bulk case, see here, your density of state in term of energy. Here both conduction band and valence band density of states are given. So here the energy terms are involved. Your density of state vary according to your energy. Okay. But in the bulk case, just now I derived, there is no energy expression. So your density of state will be constant. First thing. Okay. So see, already I derived all and we already achieved this expression. Rho E is equal to mc upon h cross square multiplied by pi multiplied by Lz. And what are these values? I already explained. Okay. mc is conduction, effective mass of electron in conduction band. H cross h upon 2 pi. H cross is nothing but h upon 2 pi. Where h is Planck constant. Pi is 3.14. Lz is dimension of the specimen. Whatever the crystal you grow as a quantum wave, so dimension of that crystal in z direction. Okay, and we we confined our crystal structure in z direction. So that direction is important. That direction length is important where you confined your crystal structure. Suppose you are confined the crystal structure for getting the quantum well structure in z direction. So in particular z direction, the dimension of the crystal structure is important. Okay. Now, comparison of density of states in bulk versus quantum well structure. So these are the expression for density of state. This is for bulk, where all the dimensions are free. Electron inside the specimen can travel in any possible direction. But here, for quantum well structure, where you confine your z direction, where electron cannot move or travels in z direction independently. So see, what is the difference? Here in the bulk case, your density of state will depends on energy E. But here, there is, in the quantum well case, there is no involvement of energy. Means your density of state is a kind of constant. Okay. So that thing is written here for the conduction band, which means E is greater than EC, minimum energy of conduction band EC, or you can say band edge energy. So there is an energy dependence in the case of bulk, but there is no energy dependence of density of state in the quantum. Present case means we are discussing the quantum well structure, which means the density of state is constant. Okay. Now we already discussed the EK diagram. So this is one figure for EK diagram for bulk semiconductor or bulk material. And here the energy variation E is vary like E is equal to EC plus H square K square upon 2 MC. This is the normal variation case. So when K is equal to 0, you will get E is equal to EC. Okay. Once the K is equal to 0, E value is in the bulk case. But for quantum well case, why we are discussing the characteristics of quantum well structure? What are the changes occurs in their band structure, their density of state? So see, in the density of state, what are the changes? In the quantum well structure, the density of state is constant, but in the bulk case, your density of state will vary according to e to the power half. Okay, this is the first point. Now let's discuss about the energy band diagram or EK diagram in both cases. So in bulk case, you will get your energy band diagram like that, and this whole band will come known as conduction band, and this whole band is known as valence band. Okay. But in the case of quantum well structure, see, your energy varies like that. EQ1 means this EQ. Q is K is like Kx plus Ky, Ikx, Ij, Ky, K, wave vector K can be written as Ikx plus Jky plus K cap Ij Kz. Okay, where Kx, Ky, Kz are orthogonal component of wave vector K. Okay, now you know that this Kz is constant and this K are discrete in nature, and correspondingly Kx, Ky, Kz is also discrete in nature, and what the value they can take, Kx will be pi upon Lx, multiplied by m ky pi upon ly multiplied by p kz will be pi upon lz multiplied by q. Okay, so this q is associated with kz term. So we already wrote the expression of energy variation in quantum well structure. See here, see this one, and we already discussed that this kz term will be constant. And why it is constant, you can see in my previous video lecture. Only the variation occurs in kx and ky. Okay, so this k is associated with kz term. So this EQ1 is nothing but this energy, and this energy is quantized. Okay, this energy is all the energy is quantized because there are the involvement of kx, ky, and kz, and kx, ky, kz all have a discrete values, and if they have a discrete value means quantized value like m multiplied by pi upon lx for kx, p multiplied by pi upon ly for ky, and q multiplied by pi upon lz for kz, and this kz is constant, so you can write this kz like that: E is equal to ec plus eq1, energy correspondingly to in z direction, eq1 plus same h cross square kt square upon 2mc. Okay, so this is your energy expression for quantum well case. Now this energy is vary or depend on kt, not k, transverse component of z direction means x and y direction. Okay, so if like the previous case what I told in bulk case, if k is equal to 0, what you are get? E is equal to ec, band age energy. But in the quantum well case, this is your energy expression, and this energy expression is depend on kt. And like previous case where we discuss if k is equal to 0, you are getting the band age energy. So here if kt is equal to 0, what you will get? E is equal to ec plus eq1, means ec plus something. In bulk case, what you are getting? ec, but here you are getting ec plus something. Okay, that is the first point. And similarly for, so suppose this is the ec, but for quantum well case your bands started from here, something greater value than ec, and this value is how much? ec plus eq1, first thing. Now you know that z is kz also have discrete value. The first value is pi upon lz multiplied by 1. The next value will be pi upon lz multiplied by 2. So here for you can also get a next band, and these bands are known as sub band. But in the case of bulk you will get two bands, two well separated bands for semiconductor, and those bands are known as either conduction band or valence band. But here you will get for corresponding q is equal to 1, you will get one band, and their lowest energy is ec plus eq1. For q is equal to 2, you will get a second band, and that band's lowest energy is ec plus eq2. Why? Because kz will have a discrete value in nature, And according, if you solve the density of state or density of state expression for q is equal to 1, you will get the corresponding expression of density of state, and the corresponding variation of density of state will occur in this band. Okay. Now for z is equal to 2, you will get one new band, and these bands are known as sub bands for this conduction band. This is first sub band, this is second sub band. Okay. So this is one thing, means there are some increment in energy band gap. For bulk case, your minimum energy occurs at EC, but here some increment in minimum energy. And what are these increment? EC plus EQ1. Then the next band, in between there is no band. Why? Because this energy values are discrete. This kz values are discrete. Okay. So don't think in between these two bands there are some bands. No, well separated these bands are. Okay, and these bands are known as sub bands of particular bands. Means suppose this is the conduction band, so these two bands are sub bands for conduction band, and the band age energy for first sub band is EC plus EQ1, and for second sub band EC plus EQ2. Okay, why? Because you can take one another value of kz, that may be pi 2 pi upon Lz, 2 pi upon Lz, and correspondingly this energy value will occur. Okay. So from this discussion, what you got? First thing, some increment in energy band gap, means in the bulk case, let's suppose this is your band age energy for conduction band, this is band age energy for balance band, then EC minus EV is equal to what? EG, your band gap energy band gap value, EG. But in the case of quantum, well, what you are getting? You are getting the some increments in band age energy, and what? Suppose this is your this value EC, but this band energy means lowest possible value of energy is what? EC plus EQ1. And here let's suppose this is the bulk case EV, but in the quantum well case you are getting EV minus EQ2. Now EG is equal to what? EC plus EQ1 minus EV EC plus EQ1 minus EV minus EQ1. Sorry, this is Q1 for first band. Now what you will get? EC minus EV plus 2EQ1. So EC minus EV is what? EG plus 2EQ1. Means what you are getting? The energy band gap for quantum well structure. Energy band gap value for quantum well structure is little bit greater than their bulk counterpart. If it is EG, energy band gap value for bulk semiconductor or bulk counterpart is EG, so the same material will show the energy band gap value EG plus 2EQ1 for corresponding quantum well structure, means there are increment in energy band gap, and that's why the quantum well structure is important for band gap tuning. Quantum well structure is important for band gap tuning. You can tune the band gap of any material by constructing the some particular shape with that material. Okay, like that in this considered case, if you are constructing or making the quantum will shape for any particular material, you will get the increment in band gap value for that material. Okay, that is first thing. And what is this? This is called band tuning of band gap. Now the next thing is existence of energy sub bands. Why? Because we are getting two types of band here. Suppose this is first band for q is equal to 1. This is the second band for q is equal to 2. This is in valence band region. This is the first subband. This is the second subband. So you can say there are existence of subbands. Okay, for quantum well type of structure, and it is not likely to be occurs in bulk semiconductor or bulk material. Now, so this is the case of comparison of energy band gap. Okay, in between. If you switch from bulk to quantum well structure, what will be the changes occurs in energy band gap? Now, density of state, I already told that in density of state, the density of state in quantum well structure is constant comparison to bulk, where the bulk, the density of state will vary according to e to the power half. So if we going to plot the density of a state of quantum well structure, and what is the expression of density of a state? C, rho is equal to mc. What is mc? Effective mass of electron in conduction band. So mc upon h cross square pi upon lz. So suppose we are going to plot the density of a state, what we will get? This for q is equal to 1. Here, suppose this is your energy band diagram for quantum well structure. Now, for density of state for this first band, in this first band, means suppose from kT to kT plus dkT, what are the energy value exist? How many number of energy state available? So let's suppose this is kT. This is your kT plus dkT. So correspondingly, this is E. So let's suppose this is E, and let's suppose E, and let's suppose this is E plus D. So how many states are available for kT to dkT for particular quantum well structure first band? First band. So it should be constant for first band. Okay. So and your energy started from, this is the minimum energy, and minimum energy value is what? EC plus EQ1. See, EC plus EQ1. So what you can say, this is your EC plus EQ1, and up to the next band means EC plus EQ2. Here KT, sorry, up to this range, the density of state value in this region, EC plus EQ1 region, available energy state in EC plus EQ1 to EC plus EQ2 will be constant. Okay, see, and why? Because the density of state is constant for quantum well structure, and its value is rho e is equal to mc upon h cross square multiplied by pi multiplied by Lz. So suppose I am considering the first band, this first band, this first band, this first band, and for this first band your density of state will be constant. It will be changed, and it will be changed for this second band. So the second band minimum energy is EC plus EQ2, and the first band the minimum energy is EC plus EQ1. So between EC plus EQ1 to EC plus EQ2, your density of state will be constant. Okay, that is my consideration. So this, see, on x-axis you are taking the density of state, on y-axis you are taking the energy. So EC to EC plus EQ1 to EC plus EQ2 energy region, your density of state EC plus EQ2 region, what is your density of state? This much. And EC plus EQ1 region, what is your density of state? This much. So this is the constant. Means for EC, for first band your density of state will be constant. Then again for next band also exists EC plus EQ3. So between EC plus EQ3 again it will be constant, and similarly so on. So your density of state diagram for quantum well structure is a kind of step like function. Okay. Okay. So this is your density of state variation in quantum well structure. So you can say density of state let's suppose this is your density of state variation parabolically in bulk case, but in the quantum well structure it should be started from here. Then so this is for your quantum well structure. So this density of state is constant for quantum well structure, but this is the bulk case where the density of state rho e varies accordingly e to the power half. Okay. So this is some comparison between bulk case and quantum well case, and their correspondingly how the energy band diagram and density of state will vary in bulk case and quantum well structure. So we discussed. So that's all for today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.